Okay, now about 70% have submit about on the poll. So most of you like just the engineer and researchers. Okay, current experience. Okay, you guys came from like some AI project and some of you came from like the model-based design. So in this session, I think okay, you will learn about you will know about how we merge this workflow together. Mm, okay, I think we can end the entry poll now. Okay, thank you very much. So at first, uh, in this meeting, in this webinar, so I will explain you about how to bring the AI and model-based design workflow to guide you through this session. To we can explore how like AI when we combine with the principle of the model-based design and transforming the way we build the and validate and deployment the AI in the model-based design workflow. So the agenda today, okay, let me begin with a quick overview of the today agenda. So at first we will start by exploring the three key tenets here, three key tenets in AI and the system, and how we like adopt the AI across the system engineering, and then we can walk through the principle approach to apply AI with model-based design. And the final one is how we will discuss about the unique value of the MATLAB and Simulink that can bring the why we need to use try to use the AI with the model-based design in the MATLAB and Simulink here. So at first, I will tell you the overview of the AI and train AI with the system here first. So at first, the first thing is the increasing of adoption is the increasing of the application of AI to enhance our traditional method. So this one is a traditional method. So here is the system level architecture diagram that help us to visualize how the different of the component of the design is include the plan models here, right? It's a plan models and controllers and perception and sensing here. So this one is quite similar to the like uh, control system, right? So we have these controllers. We can test it with the plan, and okay, we have the feedback loop with the perception and sensing by any sensors. And okay, we have this planning as the input of the controllers. Okay, this one is the overall of the traditional workflow. So how we can apply AI in this workflow? At first, for example, we can use AI to apply to the plan modeling here and use it called the reduced order modeling or ROM here, And we can take like high fidelity physical modeling that are like the computationally intense to run, and we can apply this ROM technique to reduce the complexity while preserving the model essential behaviors. As a result, so we have like model like the suitable for running the system level simulators at the large scale, and we can apply the control design and hardware loop testing, for example. The next one is the when we come to the like perception and sensing. Here's right, it's like the feedback. And then, okay, this one we can use AI to apply the virtual sensor, which is like, for example, which is the estimate the signal that came from this plant model, estimate the signal of you interested from the physical sensors. For example, some of the parameters we cannot use the physical sensors. So in this session, in this webinar, you will know about, okay, I have some example that in this case, it cannot use the physical sensors to collect the signal, collect the parameters, collect the value there. So if we compare, like, okay, in the traditional method, like we might have some command filter, right? It's command filter. You can use command filter as the like estimation for this virtual sensing tool. So today I will like can help you to compare about, okay, how we use the how we decide to use the just command filters or use the AI to apply as the virtual sensor modeling here. The next one, the third one is the, okay, we can use the technique called reinforcement learning to do to use as the planning and controls here. So this one is like we training an agent through the repeat trial and errors interaction between the agent and the environment. So most customers, the environment is modeled in the Simulink, right? And so we can able to run the simulation, and agent and environment has the interaction to train and validate itself. So this one is like the reinforcement learning that we can replace the input and this controllers here. So this one is, you see the whole workflow here is like we can replace uh, some part of it by AI technique, like as I mentioned, this plan model, this virtual sensors, and this controller and planning. Next one is a trend now is like, okay, everyone know about AI model. AI model is very large. It's a large size, and you need to have like the very big processors to tuning, to training it, and to process it, right? So you see, for example, this this one might be the common that we are using. We need, when you develop AI, you need to have a lot of memories, a lot of the processor performance, and took a lot of the powers. Like, okay, some of the AI, they need to have like data centers that it quite take a lot of the power, the electricity, for example. And now, okay, we try to reduce it. Right. Okay. We can now, for example, for the like home use or like your lab, your small one, okay, you can use GPU or CPU instead. But now what we are seeing the trend now, we go to this one, the microprocessor. So it's like, okay, as we know, when you use the AI, you need to access to the like internet. Like, okay, you're using ChatGPT, for example. Using ChatGPT, you need to take online, and okay, it will be have the conversation with you, and this one is take a lot of the power, for example. And for example, when you want to deploy to the microprocessor here. Microprocessor is very like, okay, it's very small. Okay, the memory is limited. It have constraint here. It need performance. You need to reduce it. So, for example, if you want to make this one, if you want to make this like your standalone AI in the like microprocessor, it have a lot of constraints. So today I will tell you how to use our tools to fit with these microprocessors. Next is the, okay, we have like a lot of regulation now. Is like oops, sorry. For example, normally when you are working in model-based design is, I can say, like our products, like MathWorks product, MATLAB and Simulink. So the Simulink is using Simulink for model-based design, and most of the industry, like some industry that need to create the complex algorithm. Complex algorithm, they are usually used in like automotive, aerospace, and medical device here. So from all of them is like, okay, it have a lot of regulation like ISO, and this one is the SAE here and FDA in the medical device here. So our tools if someone using the model-based design already, they might know about, okay, our model-based design, we has like the commit, the regulation and certification here. So it's quite easier to when you for example, someone came from AI part, okay, and you need to deploy and you need to create the algorithm in this kind of the industry. If you go to use the model, integrate with the model-based design, so this one will help you to, okay, automatically pass the regulation, for example, that by using our tools that, okay, uh uh it have the certification to uh, acquire this certification, for example. So this one is the three trends in the why we need to use like AI with MBD. So before we go to the workflow, so this one I will recap first about someone might not came from the model-based design workflow. So model-based design workflow is like, as I mentioned, okay, it's in the like aerospace, automotive, like energy production, industry, machineries, communication, medical device. All of them is like most of them is the like quite the complex algorithm. So we try to bring this one, all of this like to create the simple model here. It's called Simulink model. This one you can create a plan model here, and you can create the controllers. This one is like the blocks, just you connecting the blocks and try to do the simulation. So this Simulink is developed to is development the environment for modeling and simulation in the multi-domain. You will see this one. It has like in the plant model, we have the like thermal fluid, heat. Here's about the temperatures and electrification. We can merge them together to create this physical modeling in plant model here. So this one is like to is do the modeling, to do the simulation and analysis, and after this you can go for the you can bring the automation to test to convert this controllers model to be a code, and you can do the verification also. So this model-based design is will eliminate the manual step and reduce a lot of the human errors in the workflow here. So, okay, I will go to the second topics here about the how we apply AI in model-based design. So at first, from this diagram, at first I will focus the first example is the virtual sensor modeling. So virtual sensor modeling is an AI technique that estimate the signal, which is quite difficult to measure directly, or the where is the physical sensor introduced like too much cost or complexity. So I will use this use case. Okay, this use case is, okay, you will see, right? So this one, we want to estimate the signal of interest that physical sensor cannot directly measure. So what is a parameter that we cannot directly measure is the SOC. For example, some guy came from the electricity or uh the battery cell development. They might understand already about. For example, normally the in electrical parameters, normally we can use like voltmeters to measure the voltage. You can use ammeter to measure the current. You have like temperatures, thermometer to thermocouple to measure the temperatures. But for example, SOC, this one is the parameters that we cannot uh, directly measure. So it need to estimate. For example, normally you might use like Kalman filters, or it have uh, some formula, like for example, like Coulomb counting. You also use Coulomb counting to measure this SOC, but it's not too accurate. Normally, okay, we try to use it like the estimate here. So how we do that? So this one is the normal or example. Wait a second. This one is an example of the system level simulation of the virtual sensors of this battery. For example, on the right side, we have the battery model here. This one is a physical modeling, is a plant model here. And the left side, we have the controllers. And we try to do the SOC estimation by the AI model here. So based on this model, is this Simulink model, we will try to match this one, bring AI to match with the AI, the model-based design workflow. For example, this one is the AI workflow. For example, you need to do data preparation, you need to design the AI model, and then okay, after this you can do the code generation, deploy this AI model here. This was the current this the typical AI workflow. But when we merge the MBD to AI workflow, what we add is here's the simulation and testing. And simulation is test and testing. This one is something like, okay, you would like to bring this AI model to do the simulation, to do the estimation. For example, we will do the SOC estimation by AI. We will use AI to estimate the SOC estimation, and then how we validate this model does it correctly. We have this MBD workflow to do the simulation based testing on these areas. And after this, as I told you at the second trend, that everyone want to deploy your uh, small device, your standalone AI MCU, for example, it need to have like compression, that okay, you need to compress your like very large model of AI to fit with the embedded board and any MCU there. So this in this workflow, I will show on how we do this one also. And then after this is okay, deployment. So this one is the like overall workflow of merge use MBD to the AI workflow here. So what we can support you, for example, in this one, in this Simulink, and model-based design, we offer you this ready-made the AI blocks to use in Simulink. For example, you can use like this integrate some regression model or AI model, deep learning models in here. You can use like in MATLAB, we have the application called classification learners, deep network designers, and regression learners. It have many applications that help you to create the AI model from that application. And also in AI blocks here, you can import your third party, for example, like Python. You can insert like TensorFlow, PyTorch, Onyx here to use in this model-based design. Here's this one is the overall that we can bring AI in the we can bring the AI to the model-based design in Simulink. And also, for example, we also give you the specialized blocks, for example, image classifiers, or like the specialized specialized box that used with the audio toolbox here, like sound classifiers or any computer vision like deep learning object detector. You, for example, you can add YOLO into this model too. Okay. Next is okay. Not only this model, we also based on this simulation, for example, that I mentioned, the simulation and testing here, as I told you, you can bring this TensorFlow, PyTorch, or train the AI model in MATLAB and in MATLAB application, and create this uh, uh, blocks, the AI blocks, and okay, integrate and do the simulation here. So I will show the demo. how to import the TensorFlow network to Simulink and set up and running in the Simulink simulation. So here's right. At first, as I told you, we can create the deep learning model. We use the deep network designers. Here's we use the deep network designer to create the deep learning model, or we can use this one to bring the third-party blocks, third-party AI model. For example, this TensorFlow, we import here to the deep network designer, and then what we will see. Wait a second. When you import here, you will see a lot of the how TensorFlow create is like how many blocks, how many layers of the AI model here, of the deep learning model here. Like, okay, with it changed to be like featured input layers, fully connected layers, ReLU layers, and okay, we can export this model, this AI model to be the like Simulink blocks here. Okay, just save it in math file as normal. Save here, export. Here we got this one, the predict blocks here. And next, how we do this, how we do the simulation, we try to validate this AI model. How we do that? Okay, we just use some input, and okay, we can try to compare between the, okay, we will bring the input uh, to this AI blocks, the deep learning blocks here, and okay, we just prepare the data to as the import, and then we do the simulation. For example, I will fast forward here, and okay, from this one, when you do the simulation, you just need to config a bit, like, okay, we set up the step time, change the solver to be fixed step, and okay, the solver, okay, we just make it to be fixed step because of the, okay, we want to try one by one. There's so after that, we just run here. Okay, this one just change the data format a bit. Okay, we run the simulation. So we can see the simulation output on this scope here. For example, you will see on the yellow line. Yellow line is the estimation from the is the prediction from the deep learning model, and the blue line here is the simulation output from the workspace. So we will see when the cost down, areas, it have a bit of different. So after this, we will see, okay, now we can bring the AI in the simulation here in the model by design workflow. We can visualize how it different. So after this, we will show about the like model based procedures, how you validate the data, how you use another like features in model by design in this workflow. The first one is the requirement traceability. For example, after you integration, we need to verify and testing using like this requirement, the requirement toolbox. We can ensure that the traceability from AI related requirement to implementation. So we perform baseline testing. So for example, this one is like, okay, how about the AI requirement implemented? Have we done it yet, or have we tested it yet? And how about the testability between the like requirement to testing? So in requirement toolbox, this one is just the overall about, okay, we can have these tools, these requirement tools to trace between requirement here's and the model that you design and test case. So we have the digital thread that can trace it each other's. And for example, this one is the baseline testing. So it's like, for example, you want to try to test out your data-driven in this deep learning model that, okay, it came from the same parameters, and okay, you bring the condition to the real batteries and measures, and this one is like use the AI model instead, and you compare baseline testing with the with the ground truth, or this one is a lab measurement with the predict result. And then, okay, we have this one. You can use our tools to compare between the SOC baseline and SOC output here. So you will see it have, as you saw on the previous slide, it have some uh, a bit of the errors in the course down here. But you will see here it provided the tolerance here. This one is quite small tolerance. Okay, this one, okay, you can for example, at the first time that you train the model, it might not have small tolerance, small different here. But for example, when you training it later many times and make it like accurate, a good accuracy, you will got something like this. And this one is the tools that help you to validate. This one is the first one is the baseline testing in the model-based design in the Simulink here. The second one is the back-to-back testing. So this one is like we want to test the equivalence of the model behaviors between, for example, at first, normally when you do the simulation in Simulink, we call model in loop. And for example, when you want to convert these controllers to be the like the C code, C++, for example, and you want to testing about the behavior when we deploy it to be the code already. So that one we can call it SIL, software in loop. We can test it with the PIL when it's like you deploy it to the microprocessor already. This one is processor in loop, and HIL is the hardware in loop. So for this one, we have this workflow. So at first, you just create the model in the Simulink model here. You just because we have the tools called embedded coders or in Simulink coders, you can uh convert this Simulink model to be the C code, C++. You can uh, deploy it to the embedded board. Like, okay, we can test like the processor in loop, for example. This one is the workflow that how model-based design support in AI workflow here. So for example, for this formal verification tools, we also provide you this one, the deep learning toolbox verification libraries. So this one is like the tools, the additional tools that help you to verify and test the robustness of the deep learning networks there. So we also provide you the like libraries that you can test the robustness against the input perturbation there. So for example, it have some like this one is some result from this one is like, okay, you can check about your output years. For example, input, and we can test here about and see the distribution about the, for example, the blue is the in distribution source, in distribution scores, and the orange one is the out of distribution scores here, and that one is the line is threshold. So you can check by this distribution confidence scores, and about the you can see about the like how different between your AI model prediction and ground truth data. Specifically is about the like baseline testing and formal verification test here. So this like histogram is show about how closely the AI model output matched with the reference signal across the test case. So ideally, we want the most different cluster around zeros, and for indicating the accurate and stable prediction, for example. Oops. Okay. Here's next is the compression. As I told you in the beginning, that okay, for example, you want this AI model like to be the standalone AI model or you want to bring this AI model to fit with your microprocessors. For example, you create the like medical device and you want to bring this AI model to fit with your like very small device and very small microprocessor. So that small microprocessor, it have a lot of limitation, limit of the memories, limit of the performance, limit of the power consumption, for example. So after this, you need to bring this AI model to fit with this MCU. How we do that? So in MATLAB and Simulink, and in the MATLAB here, we have a lot of the technique that you can help you. It's like the first one is the structure compression and the data compression. So the structure compression here is the like from the deep neural network here. We have a lot of the technique that you can restructure the AI, the deep learning model, and make it smaller, and also the data compression. So in the, for example, we have like the tools called fixed point designers. So for example, when you done the simulation, that one is based on the variable step, is a variable to make it like the most accurate. We need to stand for the variable step solvers. And when you want to deploy to the like the MCU, the microprocessor, you need to convert it to be fixed point. And we have a tool that will suggest you, okay, for this parameter, you want this accuracy, you need to keep this parameter to fit with the which data type, which fixed point type. So we have this fixed point designer to help you. So based on this structure compression and data compression, we will see the output of it. So for example, you have this the model, the Simulink model, the AI model, and okay, you do the structure compression and data compression and then deploy. We will see how different this one is, the uh some of the output. So for example, what we want, okay, we want the errors, okay, we want it like low as possible. So for example, the original model is the errors is about, okay, it's quite same here, but the model size here, when we take like the before 16 compression, okay, the model size is smaller, about 50%, almost 50% here. And when we do only the projection compression, okay, it can like reduce about the 15%, maybe 15%. And okay, when we do both, we can reduce it. Can reduce it quite effective here. And the latency in inference latency also down here. So it have a question that, okay, does it hard to do the compression or any technique here? And if you compare, I will show you this trade-off analysis. For example, based on the example about the you do the SOC estimation. Normally, we show the trade-off between like non-AI is EKF here. And okay, this one is the AI. Like this is like litigation trees, FFN, LSTM, or LSTM, compressed LSTM here. So for example, as I told you, for in the conventional way, everyone use extended Kalman filter to estimate the SOC. So accuracy is good. Accuracy is quite good already. But for example, if you compare with LSTM, normally, okay, at first you just this one is the common of the AI technique here. Decision tree, FFN, LSTM. But what is the trade-off from the LSTM here? Is here the training speed, interpretability, inference speed, and model size here. But this one, it have better accuracy here. So that's why we need to do the compression to convert between LSTM, normal LSTM to be the compressed LSTM. So you can eliminate the model size here. You will got the model size same as EKF. Got the same size here, but the accuracy is better, is much better. So this one is a trade-in, trade-off. You need to compare about, okay, you can stay using the EKF, but if you want more accuracy, you need to try the AI instead of the conventional way. But when you apply AI, you need to have this compressed one, compressed to make it like uh, uh, more good accuracy, and the size is the same size as the EKF there. Next is the last process about in the model-based design. Okay, at first we have like requirement toolbox to help you to trace between the requirement, model, and the test case. We have like the baseline testing and back-to-back test. You can do model in software in loop, processor in loop, and hardware in loop. We have like the coverage test. We have the deploy, how we deploy this model, how we deploy to the MCU. And this one is the one of the example that after you deploy to be the C code already, and you deploy to MCU already, you need to finalize that you want to validate your model that validate your embedded coders using PIL simulation by generate this one to match with your embedded. For example, like you use like ARM Cortex, you use NXP board. We have the tools, we have the embedded coder that will deploy your model, your Simulink model to fit to be the optimized C code that fit to each brand of the embedded board here. So how we do that? Okay, at first we code generation here to be the optimized C code that match with this ARM Cortex. And okay, you can use this one, communicate with your brand model and test the processor in loop by this workflow. So how it is, for example, this one is the video. You just connect your board here with the brand model, and you just test it same like your test the model in loop. Just change the algorithm from the change the controllers from the Simulink model to be the code that deploy to the MCU already. So this one you will get like the quite same output, and you can redo the like back-to-back testing, validate for the output here. And okay, this one is like it can give you the report of the processor in loop processor in loop simulation too. So to deploy this one, normally we do the in the conventional workflow. When we create this one, our tools can help you to do the code generation with the many of the MCU, CPU, GPU, microprocessor, FPGA. We can accept all of this one. And during between the model and the conjugation, we also have tools to help you to do the model compression and both structures and both structure compression and data type compression by fixed point designers. So this one will help you help you a lot in the AI with model-based design workflow to create like your standalone AI model fit with the any processors here. So this one is our user stories. It have a lot of the customers like Goshen. They do the battery pack SOC estimation with this neural network, this AI model. Mercedes, okay, they use like the deep neural network to estimate the engine piston pressures. And Coca-Cola, sorry, uh, they uh, they create a beverage dispenser pressure. They can estimate this by machine learning. And like Cochrane Hydraulics here, they estimate the motor temperatures using these virtual sensors to estimate the motor temperature by deep learning. Here's okay. For the next topics, the second one is we finished with the virtual sensors already. Next is the ROM. We can use the ROM in replace for the plant model here. So for example, this we'll use the like system identification and reduce order modeling. For example, system identification and ROM here. This technique is used when you want to create the model of nonlinear dynamic system. But like the physical modeling is to either to the complex and or unavailable. So you can build this model from the measured data, here's from the real hardware in the system identification, or simulate data. And then from the simulate data, this one is came from like the like high fidelity data. It might came from the like third party application. Like okay, you can use like the many of the CAE, FEA tools and bring that one. But when you do the simulation with the FEA or CAE, that one is very slow, right? It's very slow, and then you need to do like the for example, this one is the you want to try to do the reduce order modeling of the jet engine turbine blade, for example. So okay, this one is quite simple. Okay, you have this plant model came from the high fidelity third party generated data. So this one is came from FEA model. It's very accurate, but trade-off is very slow. So we will try to change this one to be the reduced order modeling AI that can help you to you can do the like change it to be here and just bring the like to make it faster. For example, in FEA tools, you might take about the 30 seconds per time step, but this one is not fit with the AI HIL testing. So HIL testing is the real-time testing. You cannot use like 30 seconds per time step to use in the real-time testing in HIL here. That's why we need to convert this one to be the reduced order modeling, the ROM here. So we can use here like, okay, we have input and output, and we can create a model AI model here. So this one is quite the same one. Okay, how it different between the AI common AI model and the AI model with the with our workflow is here. We provide you the tools to create the DOE design experiment and data generation from the high fidelity model. You can bring this high fidelity model here, and we can design the DOE, and you can got the new output, uh the new output from FEA tools to feed to this AI here, that it will make it smaller and faster there. So what we have this ROM. We have the Simulink add-on called reduce order modeling here. This one will help you to do the set up the DOE here, generate input and output from the high fidelity model, and it can help you to do the training with by the AI. And okay, you can export this ROM to the Simulink, or you can uh, generate export it to be any FMU here to use it in like third parties tools. So how it used, okay, we have Simulink models. You can select just ROM for select the input and output here. And okay, you can set the DOE design of experiment, and then okay, you do the simulation and do the hyperparameter tuning here. This one is the some example from this jet engine. So example, we use the ROM application here. So we just import like the input signal from the this high fidelity model from the FEA model, for example. Just define the input and output here, and after this, you wait a second. Just define the import output here, and you just okay, just use the reduced order modeling here to create the new experiment, could create the DOE based on the input output here. So we will get this one to how you design the how you design the experimental. It means okay, how you design the your simulation case here. So you will get the distribution of the any parameters, any input and output, how it will fit with the fit with the output that will be the input of the AI model. Then okay, you can run simulation and collecting the data here, and okay, you got this one, you got the parameters, and you can create the AI models by neural state space here, and then okay, we will got the AI based ROM by using the neural network here. It's called neural ODE. So this one is the output. This is the demos. So when you create this one, you just design experimental. Just set up the constraint here, and this and this one. This one is the output of when you design the experimental already, and this one will help you to do the iteration many times of the simulation here. And after this, you will got the output. You can export it. A second. Okay, this one you also able to generate the MATLAB file from that example too. Okay, this one is the once you do the hyperparameter tuning and set up, and this one you can do the finish the simulation. Yes. Okay. I think that's all for cheers. This one is the like our user stories from Subaru. This one is quite a great example. Practice in Subaru, they can replace their third-party 1D hydraulic transmission by this AI-based surrogate model. Like as I told you, this the ROM, and the result is about 99% reduction of the calculation time, and it can enable the faster controllers design and do the real-time simulation. That is the key, is the real-time simulation. Even in the temperature range not included in training, the AI model perform accuracy and provide the generalization strength. And this is the like how it help their engineer to better workflow, faster speed, and can optimize without rely on some slow simulation. Some other case here is like, okay, we have like, if not only the AI with model-based design, we also provide you the other case like AI-based anomaly detection, AI object detection, and some learning-based control like the ROM, not ROM, the reinforcement learning, MPC controllers, or any neural network there's. The last one, why we need to use MATLAB and Simulink here to summarize. The first one is it's quite easier to integrate AI model with model-based design. Second one is the vertical workflow, that it have many workflow that space with your specific application. The third one is the V&V workflow for model-based design. It's like model compression, verify and verification, like requirement toolbox, like back-to-back testing, baseline testing, and the last one is the code generation. So you can, from the V&V workflow, model-based design workflow is quite the straightforward to design the model until the code generation. And the last one is code generation is fit with any embedded board. You can create the optimized C code fit with any embedded, any processors. And before, okay, the last one is the, okay, we can co-working with the open source. Like you see, we can import the like TensorFlow or PyTorch to create, use in the model by design and AI workflow here. If someone want to learn more, okay, we have many of the seminars or any video that you can check out. Okay, thank you very much. If anyone have Q&A, you can put it in the chat. Okay. Oops, sorry. I will check in the chat here. Okay, it has question from Douglas. Okay, what is the benefit of using virtual sensors instead of the traditional Kalman filter? Okay, that one I think I explained it already in the here's actually it depends on what you focus on. This one is that some trade-in trade-off that okay, it can use EKF the traditional ways like Kalman filter, but RSC the AI is more accurate. But okay, you need some effort to like. But our tools, we have the many tools to help you to do the like the compression model. That one it will be quite like model size same as the EKF. Accuracy is more better. Yes. Okay, from Olivier's Romeo has answered you already. Use TensorFlow with Simulink directly. Yes, it's when we can. Can we got example? Yes, this one I can share you later. How can I be sure that AI model behave the same after code generation? Okay, this one is what I show here is about the V&V workflow, about the back-to-back test. Here's that here that you can use like software in loop, processor in loop to check your model that generate after generate the embedded code already, how it matched with the like previous as you design in model-based design here. Okay. Why is the training speed marked as NTAP-A for EKF? Sorry, where it is? Because of EKF, no need any training speed. It's not an AI. EKF is a conventional ways. Yes. Okay, I think I answers all of this one. Anyone have any additional question? So the slide, this one, our marketing will share to you slide and recording. No problem. Okay, I think today have a lot of participant. 80%. Okay, thank you very much. See you later. Okay.
Thank you so much, Supamit, for the insightful presentation. So we have come to the end of our session, and we just wanted to share with you, if you're interested in our upcoming events, please feel free to go to our website where we update the latest on our events. And you can also find out about the last session of this series. So this is the third session, and next week, the next session will be the fourth session.